Hello students, let's continue from where we have left last time. So today we are going to study on impact of jet on moving curved surfaces. So in previous lesson we have discussed how to analyze if a jet is impinging on a surface that is moving either in the direction of the jet or in opposite direction. So here I have brought you the curved surfaces moving in x direction. So this is the exact what we are going to analyze today. So there's a jet that is impinging on the vane that is moving in x direction. To analyze this, what we need to understand here is the direction at which the jet is impinging the vane and the direction of the vane is not same. So to find the relative velocity, we have to use the concept of the velocity triangle or the relative velocity triangle. Okay. So let's say this is the velocity, absolute velocity with which this is striking the vane, and this is the u, that is the velocity of the vane. Okay, if you join this tip to another tip, then you get the relative velocity, right? So relative velocity is nothing but it is the velocity of the jet minus velocity of the vane. So this portion is what we call by the velocity triangle at inlet. Similarly, we can construct the velocity triangle at outlet. Let's say this v1 is the absolute velocity with which the jet is, the water is moving out of the vane. Okay, and this is the velocity of the vane, and if you connect these two top points, then you get the relative velocity, and this is the velocity triangle at outlet. I've used the concept of velocity, the triangular law of velocity, triangular law of vector addition, and the relative velocity concept to construct this inlet velocity triangle and outlet velocity triangles. So I have also written down it here so you can for your future reference. Okay, the only important thing that we need to understand here is we need to construct the velocity triangle because the direction of jet and direction of the vanes are in not same direction. If it was in same direction or in opposite, exactly opposite direction, then you can either add or subtract, but here the direction it is inclined, so we have to use two-dimensional velocity concept. You can refer the previous slides. Okay, so let's analyze this problem where a jet strikes tangentially at one tip of a moving vane. So to demonstrate the scenario, this is the exact scenario. Okay, jet is there and it is striking at the tip of a vane, and vane is moving in x direction. By the way, this condition is not there in the textbook. Okay, I just brought here so that it can give you an entire new way to think for such problems. Okay, so let's analyze this. Let's assume this is the vane. Okay, it's an enlarged vane, just this vane. It looks different, but just assume this is what is there when you strike this vane. So this is the tangential direction at this point, okay, from where water will be going out, and this is the tangential direction where water will be, jet will be entering the vane. Let's say v is the absolute velocity with which the jet is striking the vane, and this is the u is the velocity of the this is the velocity of the jet, this is the velocity of the vane. So if you connect this two, you will get relative velocity. Notice that relative velocity has to be in tangential direction to the vane. Okay, similarly, when it goes out, it has to go out tangentially. That is what you need to understand. Let's say that angle between the velocity of the vane and the absolute relative velocity is theta. Okay, and alpha is the angle between u and v. So please understand, v is the velocity of absolute velocity of jet, u is the velocity of vane, vr is the velocity, the relative velocity at inlet. So I'm now going to use u, v, and vr instead of the long name. Okay. Likewise, if you find the x component or the tangential component of v, this is the tangential component, this is the radial component. So tangential component is v cos alpha or vw. This is also known as velocity of wind at inlet. This is y component, or the radial component is the velocity of flow. Okay. When I say x component and y component, I'm loosely defining this as x because what you need to understand is x represents the tangential direction, the direction of this u. Okay. All right. Likewise, let's construct a velocity triangle at outlet. Let's say v1 is the absolute velocity that is moving out of the vane. This is the u, and if you connect this to, you'll get vr. Again, I repeat this: the vr has to be in the tangential direction if it has to leave without shock. Now there's two conditions here: the v1 with angle with which it is making with u, this angle can be obtuse or it can be acute. So for this particular case, I have taken obtuse because it is nowhere discussed in textbooks. So I thought it would be interesting to discuss here. Okay, so here I am taking as obtuse angle, and the angle that is made by VR and U at outlet is phi. Okay, in some textbook they say the jet is deflected by certain angle. To find that certain angle, you have to use the concept from here. Okay, at what angle it is deflecting. All right, so let's say this is the beta. So I was talking about the beta, and likewise we can find the x and y component of v1 absolute velocity. This is the velocity of flow at outlet, velocity of wheel at inlet. This is pretty much what you need to understand from a velocity triangle perspective to solve this problem. Okay, so this inlet and outlet, most of the parameter remains same, direction, everything remains same except for this v1. If v1 is obtuse, the orientation will be like this. If v1 is acute, then this will be something like this. So I have defined each and every terms here. Please go through this. Okay, like VW is the velocity of wind, which is the x component or the tangential component of the absolute velocity. Likewise, theta and phi are the angle made by the velocities at relative velocities with tangent at inlet and outlet. Further, let's go into analyzing this. We know that the force applied by the jet on the vane is nothing but it is the change of momentum, and further the net change of momentum in x direction, because we are talking about in x direction. So minus f of x, I believe you know now why minus f of x is coming, is equal to rho q is the mass times the velocity would be vr cos, this angle is phi, sorry, one angle phi is missing. Similarly, angle theta is missing here. Okay, so vr cos phi, it is negative because this direction, right? It's x component will be in this direction, so minus rho q vr, that is this. Okay, so vr1 cos phi means this. I've just said vr1 to just indicate that this is the outlet velocity triangle. So here I have not mentioned it, but try to understand that this one refers to the outlet section. Vr cos phi, so this Vr cos phi is nothing but this one. Okay, so that is in x direction, so it is positive, so it is here minus coming because it is change. So out momentum outflux minus momentum inflow momentum and outflow momentum, right? Further, let's put this r1 cos phi and rvr cos theta in terms of u and v. So then we get our final expression as force is equal to rho q vw minus vw1. And further, work done by the jet would be force times the velocity of the vane, so that is F into U, that will give us the force, and the work done by the jet per second would be this parameter. Further, the efficiency is the work done by the initial kinetic energy. Work done is given by this parameter. Kinetic energy is half mv square. Here the mass is the mass flow rate. You substitute that, and then you get the efficiency. One more thing we need to understand here is, if the blade angle was an acute angle, what would be the situation? What I mean is, what would have happened to our formulas if this B was an acute angle? Okay, there is nothing much will change. Only thing is VR1 cos phi. VR1 cos phi, here it is U minus VW1, but if it was an acute angle, it would be VU plus VW1. Okay, that is what you need to understand. That's it. And further, let's understand few concepts that you have already studied, but I thought it would be good to revise once again. All this slides that has star means these are the concept slides that you have already studied, but I'm just giving here for quick recap. Okay, let's understand this object is moving in circular about a point, this black dot with a radius r, then it's a linear momentum at any point would be its tangential velocity, the v times the r, right? That is the linear momentum. The angular momentum would be the linear momentum times the vector r, that would be the angular momentum. The linear momentum is, what did I say? Let me revise this. Okay, let me re-explain this. Linear momentum is the mass of the object times the velocity. Sorry about the previous, I said r. It is linear momentum is the mass of the object times the tangential velocity, that will give us the linear momentum, and angular momentum is the linear momentum times the radius vector r, that would give us the angular momentum. Further, the direction of angular momentum is given by the right hand thumb rule, which is, you just observe this figure. Okay, so now it is here, you just make your fingers curl in this orientation, and the direction of your thumb would give the direction of your angular momentum. Tau here represents the torque is given by the force times the radius vector, and likewise L is the angular momentum given by the radius vector times the linear momentum. So this is just a concept slide. So if you have forgotten what is angular momentum and torque, please revisit this concept. Okay, so for your quick reference, I have put this here so you can visit. Most important thing about this slide is the torque. The torque is, it is the rate of change of angular momentum. So that is what is torque. Okay, so more angular momentum at this position minus angular momentum at this position would give us the torque that is responsible for this object to travel from this point to this point. So that is the torque. With this, let's try to analyze one interesting thing, that is the jet striking tangentially at one tip of a moving vein. Now it is the rotational motion. Okay, it is the rotational motion. In previous case, it was moving in x direction, completely x direction. Now we are not concerned about x direction. Now let's say that the vein, once it strikes this object, this vein, it is making a rotation about a point. So this is exactly what we are going to analyze. And for simplicity, I have shown only one vein. Okay, understand that there are series of other veins as well. Okay, so there are series of other veins. Just for simplicity, I'm showing you the one vein. Okay, so let's say this is the tangential direction at this tip, and there's the tangential direction at the velocity. Okay, tangential velocity at that tip, the inlet tip and outlet tip. Likewise, quickly let's construct our velocity triangle. Okay, so this is our velocity triangle at inlet. Right, everything remains same. That is our velocity triangle at outlet. Now understand here that the V1, it's making an angle, acute angle with U1. So in previous case, I have intentionally make it obtuse to make you understand that how analysis would change if it is obtuse. So here it is acute angle. Okay, so understand there is an acute angle. This is it, the velocity triangle at inlet and outlet. It remains whatever I have explained in the previous video. All right, phi is the angle that is making between, that is the angle between Vf's relative velocity at outlet and the u. And to understand it further, I have brought here for reference the inlet and outlet velocity. The tau is the net change of angular momentum, right? The tau vector is the angular momentum flux going out of the control volume, angular momentum coming into the control volume. I'm using this control volume so that I hope you know what control volume is. But here the things are pretty straight. Okay, whatever we have studied in previous session, it is simply the continuation of whatever we have studied. And further, the zeta here is the angular momentum, and which is the linear momentum, tangential linear momentum times the radius. So the linear momentum is rho q vw1. Okay, so that is the interior radius. Interior radius means this one, right? This one, the we can go back, and interior radius means this one, from this point to this point. Exterior radius means from this point to this point. So that is what I mean. Okay, likewise we substitute this equation in final torque formulation, and then we can find the value for torque. So the torque is rho q vw1 times r1 plus v times r. Okay, so that is the torque. Further, you can omit this negative sign because the force that is exerted by the fluid on the vein, right? So in our previous session, what we have discussed is the force is calculated by the vein on the jet, right? So similar analogies here. So you can omit this negative sign, and I have given you the brief explanation here. And the work done by the jet is tau times omega. Omega is the angular velocity. Okay, tau is the angular velocity, tau is the torque, omega is the angular velocity, and the work done by the jet is given by tau times angular velocity. So you can substitute the angular velocity. Okay, you can multiply with angular velocity with this equation and substitute the at inlet and outlet, the angular velocity at inlet and the velocity at inlet and velocity at outlet can be substituted from this relationship. Okay, further you put this equation, and then you can find the work done. The work done is given by this expression. Okay, all right, it's tau times omega, and if you substitute you will get it this. And efficiency is the work done by kinetic energy. Kinetic energy is half mv square, so v is the absolute velocity. That's it. And you can try solving this problem, which says a jet of water moving at 20 meters per second pinches a symmetrical curve vane shape to deflect the jet through 120 degrees. See, is saying the jet is deflected through 120. Initial direction was this much, and it was deflected through 120 degrees. If the vane is moving at 5 meters per second positive x direction, find the angle of the jet so that there is no shock at inlet. Also determine absolute velocity of exit in magnitude and direction, and the work done. So here what we do is we start with constructing the inlet velocity triangle, then we construct outlet velocity triangle, and most of the informations are provided. Then we tend to solve this problem. Okay, so one thing we need to understand here is, due to symmetry of the vane, phi and theta will be equal, right? Because the vane is symmetrical. And here 180, right? Theta plus 120 plus phi would give us the 180, right? So this angle is theta plus 120 plus phi would give us 180. So from that relationship we can calculate that theta and phi are 30 degrees. So here theta and phi are 30 degrees. And from inlet velocity we can apply sine rule and calculate Vr. At outlet velocity, apply cosine rule and calculate angle beta. That's it. Just, it's very straightforward. Okay, all the parameters are known, you just substitute the value and you get it. Important thing here we need to understand is the work done by the jet. Work done is, in fact, it is the force times the displacement. Okay, in our case what we have used is force times the velocity, right? The thing is, we are not just calculating work done, we are calculating work done per second. There's a difference between work done and work done per second. If you multiply force with velocity, velocity means what? Velocity is the displacement per second. Yes, displacement in particular unit of time. So the unit of time we are taking is 1 second. 1 second. So the work done per second is the force times velocity of vane in x direction. So that here in unit time. Okay, so that is important here. So force time, actually you are multiplying with displacement per unit time. That's why this work done per second you can multiply with force times velocity. That's it. And to calculate work done, you need force and you need velocity. Velocity of the vane is known, so let's calculate the force. Force is what we are calculating, f of x, because that is what we are interested in. The force is the net change of momentum, like always, and f of x is momentum going out of the control volume, coming, and minus coming, momentum coming into the control volume, and you substitute the value. What is going out? What's going out now? Rho q vr1 vr, that is going out, right? So this is, since vr and vr1, if there is no frictional losses, is going to be equal. So there is no point of saying vr1 and vr, you can say vr, because it's going to be same, because if there is no frictional losses, so this 15.51 is equal to vr, so it's the same. All right, so vr cos phi and minus vr cos 30. This is this component we're talking about. Okay, and then we can calculate force. But here the question says we need to calculate the work done per unit weight, right? That's because now that the information regarding discharge is not provided. So if this is not provided, we cannot calculate the actual force. So here what we can do is we can calculate the work done per unit weight. So if you divide this equation by rho qg, then you get force per unit weight. Okay, so now if you divide by rho qg, then rho q will go, and you will have to divide the force by g, and the work done per unit weight is given by this expression, and you can substitute the value and you can get the value for work done per unit weight. Notice the unit is in meters. Okay, next thing is what we have already, I mean, it is, I believe most of we have seen this, right? So let's try to analyze this. So there is a wheel here, the jet is striking this from the, from the vertical direction, but here I'm showing you the jet is striking from the horizontal direction. The analysis remains same. Okay, the analysis remains same. So it is striking a plate, series of plate, in fact, not just one plate, there are series of plate. Here, most important thing that we need to understand is when it strikes one jet, it rotates, but at the same time, another plate comes in to replace the first plate. So the relativeness is somehow lost. So in this case, when you calculate the forces, we have to use the absolute velocity of the jet, not the relative velocity, because understand this, as soon as this plate, the jet strikes this plate, obviously this plate moves, but another plate exactly replaces this jet, this plate, right, in this position, which means it is constantly striking at the same plane, same time, at the same, I mean, it is constantly striking the plate series of time, I mean, continuously it is striking. So the relativeness is lost here. So here in our analysis we'll use absolute velocity. That's the only difference. So you can put, okay, you can, everything is known, you simply put it here and you can analyze. If I just quickly go over, force is nothing but the momentum flux going out of the control volume minus momentum flux coming into the control volume, and we are analyzing this in tangential direction. Assume that u is the velocity, that is, u is the velocity of the plate. Now here the force is rho q, the relative velocity, and work done is given by the force into u. And most important thing, what I have earlier said is you will not be using relative velocity, but you will be using absolute velocity comes here when you calculate the discharge. Okay, when you calculate force, you will use the relative velocity, yes, because when it strikes, it's also moving, jet is also moving, so there is a relativeness is there. But when you calculate discharge, the discharge, when you calculate it, you will have to use absolute velocity. Okay, discharge is force area times velocity. Yes, so here if there was only one single plate, you will calculate area times relative velocity. For series of plate, you calculate discharge as area times absolute velocity, like I have explained in previous, like I have explained just now. As this is striking, this plate moves, but again at the same time another plate is replacing it. So in the process, it's continuously striking. Okay, so it is continuously striking. So we don't use the relative velocity, but we use the absolute velocity. But when you calculate the force, yes, of course, we have to take the relative velocity here. Likewise, you can calculate the efficiency. Now, the application of this analysis is that we need to understand the application, and if you are wondering where it is applied, the dynamic, not hydrodynamic, sorry, the pumps and turbines, okay, they work on what we have just studied. Okay, we need to understand this conceptual background. We need to have this conceptual background to understand pumps, how pumps are working. So right now, this figures I'm simply showing you that interior part of a pump, there are series of vanes, and these vanes make water to rotate, and then we get the increase in head. Right now it is not important, just for information I'm showing this, that the application of everything what you have studied so far is there in pumps. Okay, so there is one question for you to think, and the series of vanes and so many other things we have discussed, right? So this is interior of a centrifugal pump. See, so there is the vanes. So these are the vanes. Whatever we have said, vanes, vanes. So many times we have said vanes, right? So this is the top view. This is the isometric view, and this is my sketch. So this sketch is, in fact, I'm drawing this part, or this part, interior diameter, exterior diameter. Now I hope from this it becomes clear to you what we are actually analyzing. So there are a few questions, okay, which I want you to try. So I upload my slides on VLE, so you can please download it and practice these problems. And if you are not able to solve it, please let me know. Okay, so this ends our chapter on impact of jet. Thank you.